Welcome to Raw History. Here, we cut through romanticization and speculation to show you, well, the unfiltered reality of human history. Beyond canvas, unsung textile heroes. When discussing World War II soldier protection, most attention goes to steel helmets, concrete foxholes, and armored vehicles. Yet hidden beneath those iconic images existed an entire world of material science innovation that protected soldiers from threats far less dramatic than bullets, but just as lethal. Winter clothing was issued by all branches of the service. The gear was sometimes in shortage, especially in winter campaigns. Soldiers at the Battle of the Bulge battled frostbite as well as their enemies. The canvas tarps and woolen uniforms, visible in period photographs, concealed extraordinary engineering aimed at protecting soldiers from extreme cold, chemical weapons, and even early detection technology. These textile innovations saved lives quietly, without the glory attached to tanks or fighter planes, yet they represented the cutting edge of wartime material science. The silent war against the elements. Trenchfoot emerged among the combat forces like a contagious disease. The first wave began in November and lasted until the second week in December. The second wave began during the German counterattack in the Ardennes. Cold injury proved as devastating as enemy fire in many winter campaigns. Trenchfoot was attributed to 5 causes: improper care of the feet, the wrong kind of footgear, inadequate winter clothing, failure to rotate troops, and cold and wet weather. The military's response involved rapid material innovation rather than simple addition of layers. The M1943 uniform came into service in the later half of World War II. The uniform was designed as a layered system, meant to be worn over the wool shirt and trousers, and in conjunction with a wool sweater and liners in colder weather. The most recognizable part of the uniform is the standardized M1943 field jacket. It was made of windproof cotton sateen and was issued in a new, darker olive drab color, OD7. This represented a significant advance over earlier equipment. The M1941 field jacket received considerable criticism. It was poorly insulated, and the light cotton shell provided little protection from wind or rain. The late war development of specialized cold weather gear, really pushed the boundaries of material science. The new gear is lined with quilted, spun glass batting made of thousands of glass fibers, each with a diameter of about 4 microns, or a fraction of a human hair. Laboratory and field tests revealed that the glass fiber lining, covered with rubber-coated nylon, actually retains more body heat, and yet is 25% lighter than present regular issue gear. This, quite frankly, represented revolutionary thinking. Using industrial materials like glass fiber for insulation challenged traditional textile applications. The new coverall suit is made of neoprene-coated nylon outer fabric, with a glass fiber batting interlining, and the interlining is quilted to the cotton twill, water-repellent lining of the suit. The Navy's development of improved foul weather gear really emerged from submarine service requirements, where topside crews faced constant spray and wind. Research projects leading to development of the new gear were instituted at the request of submarine forces. It was designed primarily for the protection of submarine crews and topside personnel on other ships. These innovations included vapor barriers that allowed perspiration to escape while blocking external moisture. Concepts that now, define modern outdoor apparel but were experimental during the Second World War. Chemical warfare's invisible shield. The spectre of chemical weapons haunted Second World War military planners. Although large-scale gas attacks never materialized as they had in the First World War, the threat drove extensive protective equipment development. The standard-issue Second World War British uniform was officially known as the small box respirator, or SBR. This mask was designed to protect soldiers from toxic gases like chlorine, phosgene, and mustard gas. Its distinctive features included a large round eyepiece for clear vision, a filter box that contained activated charcoal to purify air, and a flexible rubber face covering for a tight seal. Gas masks alone proved insufficient against many chemical agents. A majority of chemical agents are easily lethal when absorbed through the skin. As such, protective clothing must be worn. This protective clothing can be in two forms. Either it is impregnated with activated charcoal so that the agents are neutralized and absorbed by the garment, or it is sealed and rubberized so that liquids, vapors, and powders cannot touch the wearer's skin. Modern protective overgarments are made of fabric containing activated charcoal or other adsorptive forms of carbon. A complete suit typically weighs about 2 kilograms or 4.4 pounds. The fabric can breathe and pass water vapor perspiration. The challenge involved creating materials that blocked chemical agents while remaining wearable in combat conditions. In warm weather, periods of heavy exertion in full protective gear would have to be limited in order to avoid heat stress. The activated charcoal technology crucial to these systems relied on microscopic surface area. Activated charcoal has an extraordinarily large surface area, some 300 to 2,000 square meters per gram, with a corresponding plethora of binding sites. It was soon recognized that impregnation of the charcoal with substances such as copper oxide, which reacted chemically with certain threat agents, further increased protection. This material science innovation, embedding reactive particles within fabric matrices, created wearable chemical protection that saved lives without the wearer understanding the complex chemistry involved. Stealth and camouflage, the fabric of infiltration. Visual camouflage really dominated textile development during the Second World War. Camouflage became an essential part of military strategy during World War II. Both Allied and Axis armies made significant investments in creating fabrics and patterns appropriate for various battle situations. Specialized camouflage was used to help soldiers, cars, airplanes, and naval ships blend in with various environments, including deserts, woodlands, and urban battlegrounds. Yet the most sophisticated developments pushed beyond mere coloration. While infrared detection technology remained, pretty primitive during World War II, compared to modern standards, military researchers recognized its potential. Camouflage techniques using textiles have been established since World War II and have prompted textile companies and designers to investigate designs and colors best suited to the function. For example, in 1948, the U.S. Army Engineer Research and Development Laboratory created the so-called ERDL pattern. The groundwork laid during this period influenced decades of subsequent development. Modern understanding reveals just how significant World War II's textile innovations were. IRR fabric, or infrared-resistant fabric, is a special type of textile designed to reduce the infrared signature of an object or person. It does this by changing the reflection values of infrared light, so you blend into your surroundings visually and in the infrared spectrum. Though this technology matured after World War II, the conceptual framework emerged from wartime research into detection and concealment. The textile innovations of the Second World War really laid the groundwork for so much of what we use today in both military and civilian life. Synthetic insulations like Primaloft and Thinsulate were actually first created as lightweight, highly effective options for the armed forces. Now, you'll find these same materials in sleeping bags, gloves, and coats used by, everyday folks. The whole idea of layering, first developed for combat troops, has become totally standard in outdoor recreation. The military's focus on layered, modular clothing systems, with base, mid, and outer layers, has truly set the standard for what we now consider essential cold weather gear. The activated charcoal technology, originally developed for chemical protection during wartime, has, interestingly, found its way into all sorts of civilian applications. These days, modern water filtration, air purification systems, and even some medical treatments all use the same principles that were first designed to shield soldiers from poison gas. And let's not forget about those neoprene coatings, vapor barriers, and windproof fabrics, born out of military necessity, but now they're absolutely central to the performance outdoor wear we see on the market today. Perhaps most importantly, these advances proved that real protection comes from understanding threats right down to the molecular and physical level, and then engineering materials to specifically counter those dangers. The scientists and engineers who came up with things like glass fiber insulation, activated charcoal impregnation, and vapor-permeable barriers, well, they often worked in the shadows compared to weapons designers. Yet their work directly saved countless lives, defending soldiers from environmental and chemical threats that could be just as deadly as bullets. If you enjoyed this, subscribe to Raw History for more evidence-based explorations of the forgotten wartime innovations that have shaped the technology we rely on today. And hey, share your thoughts about these unsung achievements in material science in the comments below.